is moving, but the magnetic field is static. So we are going to consider a straight rod of an infinitesimally small length, dl, that is moving through a static magnetic field of flux density B, pointing in the z direction. And it's moving at a steady velocity in the x direction given by x cap and Vx as shown below. So this is a rod which we are saying it has a length of dl. We have end A and end B of the rod, and the velocity is shown moving in the x direction, and the field is coming at us, that is in the z direction, so that the y points upwards. So each free charge carrier in the rod will experience a Lorentz force that is given by Fm, given by the electronic charge. We are saying that the rod has only the charge carriers are electrons, so it has a negative electronic charge of minus q, and multiplying the cross product of the velocity and the magnetic flux. And we see that that will be pointing in the positive y direction, and it will be given by q, vx, and bz. The force will accelerate the charge carriers and will cause them to drift from the end A of the rod towards point B, or the end B of the conductor, which leads to, one, a depletion of free charge carriers in the rod towards the end A, and a free charge carrier accumulation toward end B. And therefore we will develop a coulombic force of attraction between the positively charged end and the negative charges that are moving towards the NB. And therefore, this will balance out in the steady state the Lorentz force. That is, there will be no more acceleration of the charge carriers towards end B, okay, and we have now steady state, which is a balanced case, so to speak. If you recall from your physical electronics, we had a similar situation where we had something called Hall effect. At this particular time, we're not talking about Hall effect, but we are talking about the charges themselves are being deflected or accelerated away from one point of the rod towards another, but the phenomenon is similar. So an observer that is moving with a conductor, that is, imagine yourself sitting on the conductor, and therefore you are moving with it, then you will not see the conductor as moving, and therefore it has a relative velocity of 0. It's just like when you sit in a matatu. The matatu will be moving, but you are just seated. And therefore, between you and the matatu, there's no velocity, or apparent velocity between the two of you, and therefore you are all at relative velocity of 0. So you'll just be noticing that the matatu, as far as you're concerned, is at standstill, so to speak. But to an observer outside, he can see that the matatu plus the passenger is moving. So the observer will therefore only detect, if he was to use a voltmeter or a field meter, the only thing he can detect is the balancing static electronic force or electric force per unit charge, and this will be given by E prime, given by Fm divided by the charge on a carrier, and we are leaving the negative side on this side, so that we have negative of V cross B. Now, the only way he can interpret this electric field is that it's an induced electric field that is acting along the conductor. And it will therefore establish a potential difference across the conductor from end A to end B that is given by the negative of the integral of E prime over the length dl from A to B. And we see that that is just going to be V cross B dot dl integral. Now, if the inertial conductor, by inertia we are saying the moving conductor, is part of a closed circuit that we call C, The EMF generated around the circuit will therefore be given by Vm equal to the closed line integral over that curve or over the circuit length of V cross B and dl. And therefore, we refer to this as a flux cutting EMF or a motional EMF. This is the working principle behind an electric motor or an electric generator, so to speak. So we note that the only part of the circuit that moves, that contributes to this Vm is that part of the circuit that is not moving in a direction parallel to the magnetic flux. Okay, and therefore it will be cutting the flux, okay, to generate that Vm. If it was moving in parallel direction, then the V cross B would be identically equal to 0. So, a metal bar, that is an example now, a metal bar slides over a pair of conducting rails in a uniform magnetic field B given by Z cap B naught with a constant velocity V as shown in figure Q2. This is our figure. This, you can remember, it's more like, we call it a linear motor. It's just like the usual motors, but with the armature or the rotor, the stator. The stator is straightened out into a rail, and the armature is just a straight road, and it's just crossing across the whatever over the rails themselves. So our value or our conductor is moving in the positive x direction, just like we had before. It has a length of h between the conductors, that is where the contacts are. Although it's shown here with a finite thickness, let's just assume that the h is where the conductor, our conductor here, contacts the rails themselves. And therefore, again, we know that the Lorentz force and so forth will cause an accumulation of charge towards this end and a depletion towards this end, and therefore we can measure a static or an open circuit voltage between the two rails as shown. Now, the question is, determine the open circuit voltage VOC that will appear across the terminals 1 and 2, and B, determine the electrical power that is dissipated in a resistor of resistance R connected between terminals 1 and 2, and then show that this electrical power will be equal to the mechanical power required to move the sliding bar with a velocity of V. We are asked to neglect electrical resistance of the metal bar, as well as the conducting rails, and as well as the mechanical friction that would appear or would always occur at the contacts. So the bar generates a flux cutting EMF, and we are going to say that that is going to be given by VOC equal to Vm1 minus Vm2, where this is the terminal 1 and that is terminal 2, and we get that the negative of the line integral, closed line integral of V cross B and dt. And we get that value is just going to be V0, and multiplied by the separation distance between the rails. With the resistance R connected, then we would have a current V0, VOC divided by R, and we'll therefore get V0 or V0, B0 H divided by R. And it will flow from terminal 2 to terminal 1, where we have assumed that the rails are perfect conductors as we have been asked to ignore the resistance, and therefore the electrical power dissipated in R is just going to be given by the usual equation for electrical power, which is I squared R. And this we get as R multiplied by that all squared, and we get that V0, B0, H squared divided by R is the power that we are going to call the electrical power. The mechanical work done per unit time in moving the metal bar per unit time is given by Pm equal to Fm multiplied by V, where Fm is the mechanical force that is acting on that rod to move it. So, and it is used to counteract the magnetic force Fm exerted by the flux cutting. So, we have Fm equal to I, the integral of dl cross b. This is from the Biot-Savart law, and we get that I, y cross z, and b naught, and dl gives us a minus x cap, L, b naught, and h newtons. Hence, the Fm is going to be the minus of F of m, and this we get it as shown there. And the power, mechanical power that will be dissipated or work done per unit time is going to be equal to the work done per unit time in the electrical case. And this therefore tells us there is conservation of energy, as we have been so told in physics. Another example is what we call a Faraday disk, that is usually found, especially if you looked at the old electrical meters from Kenya Power. They used to have a disk that is rotating inside, okay, to try and count the number of revolutions that is making per second, to tell how much power you are taking away from, or how much energy you are taking away from the network. So a Faraday's disk generator consists of a circular metal disk that is rotating at a constant angular velocity omega in a uniform and constant magnetic field of flux density B given by Z cap and B naught. And this is parallel to the axis of rotation. That is, if the circular disk is horizontal, the B will be vertical. So the brush contacts are then provided at the axis and the rim of the disk. Determine the open circuit voltage of the generator if the radius of the disk is given as B. Now, this is how it looks like. So the axis of rotation in that direction is at the center of the axle. Now we have a contact here and a contact there, which we are calling 1' and 2'. And this 1 and 2 are the terminals where we are going to measure our voltage. We are saying that the rotation is in that direction, in omega, and now we put in here a circuit, okay, that is given by 1', 4, 3, 2', and then 2. So that's our circuit that we are looking at. But we look at the connecting distance here, radius, which is just B, and this is what will be cutting the flux, because the flux is pointing in the vertical direction. So we are just interested in this radius here that is cutting the flux. So we consider the closed path 1, 2, 2', 3, 4, 1', and 1. So of the part of 2' and 3, 4 that is moving with the disk, only the straight line 3, 4 will be cutting the flux, the magnetic flux. And hence, V naught or VOC is going to be given by the line integral of that circuit. So our C is therefore 1, 2, 2', 3, 4, 1', and 1, and V cross B dl. And we see that only 3 to 4 will be cutting the flux, and therefore the VOC is only contributed to by only this integral. And we see that that integral is going to be given by phi cap, that is the direction of the azimuthal directional vector, multiplied by r omega, giving us the velocity, times the z cap and b naught, multiplied by the arc length, or the element of length that we are dealing with, that is dl. And once we do that, we'll get a value of minus omega b naught multiplied by the radius squared and divided by 2, and this will be in volts. So we look at now a circuit that will be moving in a time-dependent magnetic flux. That is, we are now looking at the general case where we have a charge Q moving with a velocity v in a region where both E and B exist. That is, the electric field is existent and the magnetic field is also existing in that region. And therefore, this charge will experience an electromagnetic force F, and this will be given by the Lorentz force equation, which we have here as F equal to Q E plus V cross B. We call this equation of motion, okay, is something we have already met in physical electronics, and this is where we were talking about the Hall effect, so to speak. So this is where the force is. So an observer moving with a charge, now we are not looking at the circuit itself, we are just looking at the electron or the charge carrier, and we are sitting on it, and we are moving with it. So if we are moving with it, then we don't notice any apparent motion between us and the charge. And therefore, the observer will only detect an electrostatic force that will be acting on that charge Q, and will interpret the force per unit charge as an effective electric field intensity, which we are going to call E effective, and will be given by E effective equal to E plus V cross B. It's just this equation. The E effective is just F by Q, and this is what we have here as E plus V cross B. Now, the field intensity that will be measured in the stationary or laboratory frame of reference is hence, that is, we are saying that someone else or an observer is looking at us and trying to measure our circuit or our charge, and to measure the whatever the electric field. So all the person will be getting is an electric field E in the region where this charge is moving, and therefore it must be given by E effective less the flux cutting, or the V cross B, the magnetic force. So for a conducting circuit that is defined by a closed contour C of enclosing a surface, an open surface S, that is moving through the field E and B with a velocity of V, we can write therefore that the line integral, the closed line integral over C of E effective dl must be given by the E that we have from Maxwell's equations or Faraday's law, okay, plus the line integral of that motional force per unit charge coming through the motion of that charge. And this is therefore referred to as the general statement of Faraday's law of induction for a circuit moving through a time-varying magnetic field. So the EMF induced in the moving or inertial frame of the reference, that is a coordinate system moving with the circuit, is given by V effective equal to that line, closed line integral over E effective. The transformer EMF due to the time rate of change of the magnetic flux density is given by the VTX equal to the minus of integral d dB dt equal to dot ds. This is what we already saw before. The motional EMF due to the motion of the circuit through B is then the term dm equal to that closed line integral of V cross B. What we can say, or what we should put in mind or have in mind, is that what is transformer and what is motional EMF will depend on the frame of reference that we have chosen to observe our system. Say, for example, if you could have a laboratory that is moving with a charge, then The guy who's in a stationary charge, we will see him as moving in the opposite direction as us, and therefore for him, we can always define a motional EMF for him, so to speak. And therefore that is something you have to put in mind, because this is where physics becomes very sometimes mind-boggling, so to speak. I'm sure you have always been perplexed, say for example, in a jam and a big lorry parallel to your matatu, and you are stopped. When the lorry starts moving, you can feel like you are actually moving backwards, okay? While the matatu would just be at standstill, so to speak. This is the kind of effect we are talking about. Now, in the general case, we look at a closed circuit, which we are calling C1, and it's moving through space in that direction, given by V delta T. So consider a rigid, this is a very important word, rigid conducting loop, moving with a velocity V through a time-dependent magnetic field of flux density B as shown. So our circuit was at time equal to 0, at t equal to 0, we were at C1, and then after a short time interval, delta t will be at the position of C2, but it's the same circuit that is moving. The reason why we are saying it's rigid, we don't want it to change its shape so that S1 and S2 are equal. Okay, it does not deform. So the surface S1 therefore moves from C1 to C2 over a time interval delta t. The motion may include any of the following, that is translational motion through space, just like we have shown. It could be a rotation about an axis, which we had seen before, or a distortion of the closed surface. That is, the surface itself can be deformed, but this we have taken out of the equation by requiring that our loop be rigid, that is, it does not deform, and therefore this will not be considered. So if you are to write down Faraday's law of induction, and we look at the rate of change or the time rate of change of the flux, d psi dt is going to be given by d dt of the integral of the charge or the magnetic flux density over that surface that we are dealing with. And this can be given as a limit as delta t goes to 0 of 1 by delta t, and the integral at S2 for the field at S2 will be b t plus delta t and delta dot ds2 minus what it was at the position of S1. If v and delta t are sufficiently small, then we could use Taylor series expansion and write the flux density at S2 as approximately given by the flux density at S1 plus delta t multiplied by the time rate of change of that delta B, or of that magnetic flux density. And therefore, we can always write that the total derivative of the magnetic flux density, okay, the integral or the total derivative of the magnetic flux is going to be given by that value plus the limit at delta t goes to 0 of that equation there. Okay. So the side walls, that is, as the circuit is moving, it's sweeping out a volume given by the cross-sectional area S1 and multiplied by the side wall S3 given by the value of the velocity multiplied by delta t. And therefore d S3 is defined as the element of length multiplied by the velocity, or the element of, the height of our cylinder, so to speak. So we apply the divergence theorem on B in the region to obtain that the integral of the divergence of B over dV is going to be given by the surface integral of that value at S2 minus the surface integral at S1 plus the surface integral of this S3, that is the sidewall. The sign on the integral over S1 is negative because the divergence theorem assumes the outward normal on the given surface. And therefore, on the surface S1, it will be pointing outside the volume described by the moving volume, the moving circuit. But we recall that there are no magnetic charges, and therefore the divergence of the magnetic flux density is identically equal to 0. And therefore, we can write that that equation must be equal to that equation given on the other side. And therefore, you can write that the time rate of change of that flux, then a flux is going to be given by that minus cross V cross B and then dl. The EMF induced in C as measured in the moving frame is of course the V effective, and we say that this would be the effective electric field that will be measured by anyone moving with the circuit. And we can therefore write that V effective is equal to the closed surface integral of E effective dl, and it is going to be given by the time rate of change of the flux density of the magnetic flux, and we get it as minus d phi ds. And this is the equation that we have always met when we deal with transformers or we deal with generators and so forth. So question, example 4. We have a coil or a loop that has a length h and a width w, and it's rectangular, and it's placed in a magnetic field that is sinusoidally varying with time. It has a constant amplitude b naught and moving according to sine omega t. The normal on the loop initially forms an angle alpha with the direction y, as shown in this figure below. The normal on the surface is actually coming away from the surface, perpendicularly to the surface, although it's showing here as it's moving, as if it's moving parallel, but it's actually coming out of the surface of the plane of the loop. So determine the induced EMF in the loop A when the loop is at rest, that is the loop is resting, and B when the loop is rotating at an angle or at an angular velocity omega about the axis, where the axis is of course parallel to the x direction. So when the loop is at rest, we have that the flux that is threading that surface given by the rectangular loop is just going to be the integral over the surface. And we get it that it's going to be b sine omega t times the normal vector on the s itself multiplied by hw, where hw is the area of the loop. And we see that that is just going to be given by hw b naught and sine omega t multiplied by cos alpha, and the cos alpha is the angle formed between the y direction and the normal or the normal vector to the surface. And therefore, the voltage VA is going to be given by the negative of the time rate of change of the magnetic flux, and is getting as the minus of h omega or hw b naught omega and the cosine of omega t, and multiplied by cos alpha. And therefore, this gives us what that value is going to be, where s is just h multiplied by w. Part B. When the circuit is moving, then we'll have an E effective that will be generated or will be measured by anyone sitting on the coil and moving with it, or on the loop and moving with it. And therefore, this will be given by what we have already seen before. And we see that the first one will be the value that we got at rest plus the motional EMF that will be induced around the circuit C. And the V cross B is, of course, given by that value, where we are just adding those. And we have the value coming as twice HW by 2 omega B naught sine omega T and multiplied by sine alpha. The sides 2, 3, and 2, 4, this will be shown on the circuit itself. I am a few steps ahead, so I don't see how I'll go back and show this. I think we can see that after we have gone through the example. Then we say that when alpha is equal to 0, at t equal to 0, then we can always take alpha to be the same as the value omega t of the rotating loop. And therefore, that line integral becomes just simply sine squared of omega t and multiplied by omega s and b naught. Remember, s is just h by w. And the total EMF induced in the rotating loop is therefore given by V equal to omega multiplied by cos 2 omega t. When we differentiate that, therefore, with the value of the flux. So psi is just going to be given by that value, and we see that that is going to be given by sine 2 omega t, and to compute V, we have just that value there. So one of the important laws that we will find very useful in working through the electrodynamics is what we call Gauss law. And this states that the total electric flux emanating from a volume V through a closed surface S bounding V is equal to the net charge enclosed within the volume. That is, we'll have a volume V, then we'll integrate the electric flux around that surface that is enclosing V, and if we do that, we shall know that inside the volume we have this much charge. This is the beauty of electrodynamics, that is, we can tell what is inside somewhere by just integrating around the surface. It's more like knowing what is being cooked in the kitchen by just walking around the kitchen surface or the walls and smelling the smell that will be coming out. And you can always tell how much cake is being baked in there, so to speak. So let rho be the volume charge density, okay, per unit volume in the volume V. And therefore, what all Gauss law says is that if I was to integrate the electric displacement or the electric flux that is coming out of the surface must be equal to the integral of the volume or the charge, the total charge inside that volume. That's all it says. Now, we are got this surface integral looks weird, and therefore we can always change the surface integral into a volume integral using the divergence theorem that you met in the third year. So when you look at this, we call this a mathematical statement of Gauss law. It's exactly what that English statement is talking about. So the divergence theorem will therefore allow us to convert this closed surface integral to a volume integral. And the divergence theorem, we repeat here, although if you remember it, of course, you don't have to worry about it, but we'll just repeat it for completeness. And the divergence theorem states that the integral of the normal component of a vector field over a closed surface S is equal to the integral of the divergence of that vector field throughout the volume V, whose boundary is S. Remember, all we are interested in is the surface. The volume could be arbitrary as long as it has S as a boundary. So we'll express this in a mathematical form as follows, that the integral, the closed surface integral of a vector field D over the surface is equal to a volume integral of the divergence of that vector field over the volume. And since we have this equal to rho, then we can just equate those two together. Okay, so this first part is the divergence theorem, and the whole of it now is the Gauss law. And therefore, since we have only restricted V, that V should only have S as its boundary, then it's arbitrary. Okay, our choice is arbitrary of V as long as S is the boundary. And therefore, this divergence, this integrand here, must be equal to the integrand on the other side, because from mathematics, we've been told, or we have found out that the two integrals are equal if and only if the integrands are equal. That is, if the integrals are over the same limit. And therefore, it means that the divergence of D is equal to the charge density or the volume charge density inside the volume. That is del the divergence of D equal to rho. This we have met many times. And this is one of the auxiliary equations of Maxwell. Now, we have seen what the magnetic field or the electric field is defined. We have seen that the curl of the electric field is equal to the negative time rate of change of the magnetic flux density, and we call that the Faraday's law of induction. We have also seen that the divergence of the electric flux D, or the electric displacement D, is equal to the volume charge density rho. So for the electric field, we can say that we have two definitions, and now we want to see how is the magnetic field defined. So the vector source of a magnetic field intensity H is usually an electric current. An electric current, we know from basic whatever definitions, that it's just moving charge. Okay, the current will be charge per unit time that is moving around, and it will induce a magnetic field. So this will always consist of a conduction current that would get, say, for example, in a conducting wire or a copper wire. And this will be represented by a current density Jc, and this is due to the free volume charge flowing through the conducting medium. 2, there will be a displacement current, just like what you usually get in a capacitor that is biased with a time varying voltage. There will be a current that will be flowing through the capacitor, and this is just called the displacement current. And this is going to be given by the charge current density Jd of the time rate of change of the electric flux or the electric displacement D. And this will arise from the time rate of change of the charge density in a given volume. Then we have another kind of charge or current that would come, especially when we have the charges moving through space, just like wind, so to speak. If you were to say that the atoms of air are ionized, then they are moving in the wind, they will constitute a current, an electric current. This is called a convection current, and the current density Jv will be given by the volume charge density rho multiplied by the velocity with which it's moving. Okay, and this in many cases we are going to ignore, because this is usually important, especially in the layer of the atmosphere we call the ionosphere, where the air molecules are ionized by cosmic rays and UV light, to form free electrons and free gas charges. They are called a plasma. Such a fluid that is charged would be called a plasma, where the negative and positive charges are equal, but they are not, they are separated, so to speak. So the total current density due to charge motion will be given by J, and this will be given by the conduction current JC plus the current JV. Remember, the displacement current density is not a moving charge, but it's a charge that is changing with time. That is, the density is changing with time. That produces JD, and therefore it's not included in this equation. So whenever we have J, we have in mind that J consists of a conduction current density plus a convection current density. For our case, like I mentioned before, we are not going to worry so much about the convection current. We shall have only the JC, and we'll drop the subscript. So we can say that convection current, like I said, is important when we are looking at plasmas, and plasmas, we have said, are fluids where equal charges of positive and negative charges are moving and find themselves in the same region of space. So Ampere's law is based on the circulation of H, and we say that the circulation of the magnetic field intensity H around a closed contour C that bounds an open surface S is given by the surface or the line integral C of a closed contour H dl is equal to the surface integral of the time rate of change of the electric displacement over that surface plus the total current flowing through the open surface S, and we give it as J ds and integral. Now we apply Stokes' theorem to convert the line integral into a surface integral, just like we did with the divergence theorem for electric field. So when we use Stokes' theorem, and if you recall, we already said that the integral of the curl of a vector field over a given value, or of a vector field over a closed surface C or a closed path C is equal to that normal component over S, and therefore we can put that all through. And again, we say that as long as S is defined to have C as its boundary, then these S's are all the same, and we can now drop the integrals. And we have that the curl of H is equal to the displacement current density plus the conduction current density, or the total current due to moving charge. Remember that J could have JC plus JV, but in many cases we shall just have JC alone, and therefore we have dropped the C, the subscript. Now, because we have no physical magnetic charge, none has been found, the smallest magnet will always have a north pole and a south pole, and it's formed by closed lines, okay, magnetic flux lines. The smallest magnet being the electron, due to electron spin, and it will always have a north pole and a south pole. And therefore, you can say that there are no isolated physical charges, and therefore, if we take the divergence of the magnetic flux density, we must get it going to zero, because for the divergence, we are looking at something emanating or going into, therefore there must be a source or there must be a sink where that whole thing is going through. And therefore, we call the magnetic field density intensity is a solenoidal or whatever vector, or it's a divergentless vector field. Solenoidal in the sense that in a solenoid, the fields are the magnetic lines of flux close on themselves. So the four equations from this discussion are called the Maxwell's equations in the differential form, and we summarize them as follows. One, Faraday's law of induction, that the curl of E is equal to the minus time rate of change of the flux density, magnetic flux density. Two, there is a general Ampere's circuit law, which is given by the curl of H is equal to the time rate of change of the electric displacement plus the conduction current. And now, this first part, if we were to block it, we would get the static magnetostatic field that the curl of H is equal to J that you already met in third year. Introduction of the displacement current was a major contribution Maxwell made in the understanding of electromagnetic fields. Okay, without this, we found that the Maxwell's equations or the equations would be not consistent, and we shall show why. Then we have met what we call the Gauss law, and we saw that the divergence of the electric displacement is equal to the volume charge density, or the net volume charge density. And finally, we have shown that the magnetic flux density is solenoidal in nature because its divergence, the divergence of the magnetic flux density, is identically equal to 0. Those are the four Maxwell's equations that will be important to us. These two are called auxiliary equations because we can always derive them from the equations we have here. They just support. And we see that the reason why we are putting them in, we shall see, is because of Helmholtz theorem, and we shall be meeting that in a few minutes. So, the introduction of the electric displacement current density is a major contribution from Maxwell, and this has allowed us to formulate the electromagnetic wave equation, usually referred to as the Helmholtz wave equation. So, I'll stop here first so that you can see whether there are any questions. Anyone who has any question can, so far, can actually talk or can ask, and we can go from there. Then I'll give you a 5-minute break so that we can continue. In fact, I'm almost finished anyway. My time is almost ended. Any question? Is it safe to assume I'm all alone in this class?
We're here.
Yeah?
We are here. We're listening.
You are so quiet. Okay, so then I'll, since you don't have any question, then we can actually try to look. I'll blast off and see where we'll reach so that we can look at what we call the reduced Maxwell's equations. Or do we break and we meet next on Thursday?
Yes, we are actually out of time. We only have 10 minutes.
I have 10 minutes, yes. And 10 minutes is still my time. I can use it the way I want to use it, isn't it? So anyway, I'll give you the break. Then we'll continue from there next on Thursday. And what we'll be looking at are what we call the reduced Maxwell's equations. And by reduced Maxwell's equations, what we are going to do is that we know that the fields are going to be three-dimensional. So we are going to choose one dimension to be an axis, and then we shall describe the fields in terms of field components that are normal to that axis and field components that are parallel to the axis. And this will give us what we call reduced Maxwell's equations. And while we have only 4 equations or Maxwell's equations, when we use the reduced form formulation, we shall find that we'll increase the number of equations that we have. But they are usually much better to use, because then as we go along, we shall be classifying how our electromagnetic field is like. Okay, we can give them names or classes, and it makes it easier to analyze. So that's all I can say for now. There's someone who is asking for class notes. I'll be giving you the class notes at the end when we are through with it, or do you want them now? Yeah.
Afterwards is okay.
Yeah.
After this class.
We can go now, because what happens is that if I give them beforehand, you may get the illusion that now you don't even need to come to class, you have the notes, isn't it? And then it becomes very difficult for you, especially when you try to go through my formulation. I want to introduce my formulation, then you guys can see after that to see how it really all comes about. Okay? So without disappointing everyone, I'll always be giving you this at the end of every slide that I have. So with that, then I'll wish you a good day, and let's meet on Thursday then.
Excuse me, sir. Could you share the recordings for these lectures, today's and last week's lectures?
Yeah, those ones, the recordings usually take a bit, they are actually delayed. Maybe I can get the ones for last week, but this one of today will be arriving for some time later.
That's okay then. You can share the one for last week, and when this one comes, you can share it as well.
Yeah, okay. Maybe what we can do is that I can make whatever folder in the Google Drive, then I'll share that folder. Is that okay?
Yeah, that's all right.
Yeah. So, okay. Have a good day then.
Excuse me.
Yes?
Could you avail the notes for after every lecture? Could you avail the slides of the lecture that we have just had?
Yeah. Well, that is going to be a challenge, because what I have is that every topic I've put it into a document. So until I'm through with this document, this one is not going to be available. But you can try to follow it from the videos as you have asked. Okay.
Okay.
I'll give it after I've gone through it. I'll then give it to you to look at. Okay. But before we are through this particular part, it's a bit difficult for me to actually give it, because I haven't made them into lecture forms. I've grouped them together, so that I go through once and then I give that as a complete package. Okay?
Okay.
Yeah. And there is someone who is trying to join now when we are leaving, and admit him, but we can just meet then on Thursday. Okay, thanks for listening. And I hope I am not losing anyone along the way. Stop recording.